Everyone, let's give a round of applause. Kevlin.
Okay, so good afternoon. I have the after lunch slot, which is where you want to sleep. Hopefully you've had some good food. This is a talk about the full stack. Actually, it's a talk about the fuller stack of pancakes. Today is Star Wars Day. May the 4th be with you. Thank you, good. So I chose a Star Wars font, and there's my social details in Star Wars Star. I think that's the last Star Wars reference we're going to have here. So, what is this talk about? This talk is about 45 minutes. That's what it's about. It's about the fuller stack. We often use the term full stack. I went on LinkedIn just to see what I would get for full stack developer in Bucharest. It's a lot of results. We are looking to complete our team with passionate people. You see, there's a whole thing here. This is from The Economist. Passion is becoming a requisite for professional success. I'm not entirely sure if this is how we're supposed to make baby programmers or something. But I also need to remind you that the original meaning of the word passion is suffering. The Latin for suffering. That is why compassion is compassionate. It is to suffer with somebody. That's what makes it compassionate. But I think passionate developers who are suffering also makes sense. Now, interesting enough, there's a trend here. I've noticed it over particularly the last 10 years. And they analyzed it here in The Economist. New analysis of job postings in America found the proportion that mentioned passion rose from 2% in 2007 to 16% in 2019. Well, interestingly enough, I did my own interval check on this one in the UK, because I talked about passionate development in 2018. In 2018, in the UK, passionate software developer, nearly 6,000 results. But this year, 33,000 and some. That's a lot of passion. There's been a huge increase over the period of the pandemic. Now, we should actually look at this, because one of the things I want to talk about, when I'm talking about the fuller stack, I want to give you the sense that what many developers call the full stack is a very small part of the overall stack of both technology and what makes technology work, the socio-technical side. There are people. They are above the stack. How we think about people, how we work with them, is vitally important. And this is a key idea. What psychologists call harmonious passion, genuine enjoyment of an activity, is a good thing. That's the kind of passion I think we want to feel. Obsessive passion, compulsion to do something, not so much. That is dysfunctional. But I get the feeling that that is also what we're being encouraged to do in our workplaces. So, this idea of demonstrating more commitment than competence is a problem. There are a lot of people who are passionately committed. And yet we don't need more passionately committed people. What we need is people who are deriving enjoyment from their work, but also are good at it, competence. There's no substitute for that. The ability to focus on what it is in the stack that makes our technology work. And one of the observations, this manifesto is over 20 years old. And a number of people go, well, it's over 20 years old, Agile has moved on. Let's look at these words. They're actually quite good. There's nothing here I would disagree with. You know, I still value individuals and interactions over processes and tools. I still think that working software is a great idea. I don't think anybody's going to speak against that. I also think that kind of hanging out and talking to people like your customer is also a good idea. And likewise, responding to change. That has not changed. Anybody who thinks the Agile Manifesto is out of date is wrong. But the way that we talk about it, now that's a problem. Let's look at this. Individuals and interactions over processes and tools. I see an awful lot of stuff these days that's all about processes and tools. Certification. Oh, lots of certification schemes. You talk to some people and say, tell me about your process. And they say, yeah, we're Agile. We've got Scrum certification and we're using Jira. You just told me about processes and tools. You didn't tell me anything about your people. You didn't actually tell me, is it a nice place to work? Do you have a good vibe in your environment? Are people helpful? That's what makes software work. That's the top of the stack. Okay? This is really important. This lovely observation about 10x developers from Brandon Schwartz. To be a 10x developer, be a good developer who helps 10 others get better at what they do. That is the kind of thing that we want. So let's go back to the technology. I found this last year. Somebody observed that this logo is a way of annoying two different communities at the same time. Just out of interest, anybody here work with Java? Okay, anybody here work with JavaScript? There you go, and there's an intersection there, and they're probably quite angry or confused. So when we talk about this, you hear people, oh yeah, front end, back end, and then we call this bit full stack. But I would like to point out that there's an awful lot of stuff down there. See, my background is I worked in sort of embedded and real-time systems and middleware. That's my background. I was used to, so a few years ago when somebody said, oh, I'm a full-stack developer, it's just like, oh, so do you do kernel work? Do you write drivers? No, I talk to databases and I put stuff on screens. Oh, okay. So you actually ignore most of the stack, right. It's a tiny, tiny little bit. Full-stack development. It's a tiny, tiny bit in the middle. And then to get a real sense of everything else that goes on. All of this stuff. This is where the people are. Down below, by the way, the bottom below the screen, that's the physics. I visited a company last Monday, and they do quantum computing. It's the first time anybody has introduced themselves as, hi, I'm a quantum engineer. It sounds like, Marvel Cinematic Universe. But the best bit is I said, so what do you guys do? And they said, we do full stack development. They do, all the way down to the atoms. That's the fullest stack I've ever seen anybody. So next time you're introducing yourself as a full stack engineer, just think, am I doing quantum mechanics? Probably not. So this is this observation. Development needs to go further than the technical stack. We need to go all the way down, but also all the way out. We need to appreciate the impact that physics and people have on what we're doing, because it makes a difference. We're very technology focused, which is natural. So I want to give you a little scheme, a little system of classification from 1980. This is a system of classification from Meyer, Manny, Lehman in a wonderful paper that is now nearly 45 years old, but seems to have had a very good grasp of what the future could hold. And this system of classification is kind of a useful one. S programs, P programs, and E programs. So what's an S program? Programs whose function is formally defined by and derivable from a specification. So if you've got code that is S code or S systems, that's classic formal spec stuff. That's stuff that if I tell you what I want, I can understand the nature of the system I'm going to build. That is pretty much everything. This is the logic stuff. In fact, this is a wonderful graphic novel. It's very much about the quests in logic and mathematics at the end of the 19th and the beginning of the 20th century. It's also very much a biography of Bertrand Russell. And it talks about the philosophy and the mathematics of the time. It's a really good graphic novel. But one of the things they define in there is a very nice definition of algorithm. S programs are very often very algorithmic. A methodical step-by-step procedure described in terms of totally unambiguous instructions which start at a specified initial condition and eventually terminate with the desired outcome. Now, I want you to hold that definition in your head. We're going to come back to algorithms in a moment. But S systems are not just about this. It's not just about toy computer science problems. There are many problems that look like S-shaped problems. If I asked you to develop an accounting system, the rules of accounting are specifiable and known. There are laws and regulations at the national and international level. There are no surprises here. Oh, there's subtlety, but there's no surprises. These rules are well defined. Many of the things that we do are well defined. S-type code is also easy, or relatively easy, to test. You have an expectation. The specification tells you, not only gives you ideas about how you can implement it, but it also gives you a sense of how to test it. You can determine the outcomes. And if you can't, then that gives you the questions. You're able to know an S system. An S system is knowable. And that's great. But that doesn't mean we're good at it. Let me give you a very simple example. Okay, who's done online transactions? Yeah. And you've probably gone to enough websites, and you put in your number, and then you get this. Payment card number must not contain spaces. Why did you put the spaces in? I mean, I put the spaces in because I am human. Because on the card is printed 16 digits, but humans can't read 16 digits, so we do things called chunking. We visually separate these, we put spaces in. That is how it is presented. So I type it in so I can also see that I put in the right thing. And then somebody writes a piece of code, and they had a choice. And I'm going to ask you to think about this for a moment. They could have just replaced the spaces with nothing. That is algorithmically very simple. I want you to think, how hard is it to eliminate spaces from a string? Okay, land a human being on the moon, remove spaces from a string. This is your classic S-type problem. But I also want you to think for a moment, how much development effort went into detecting that there were spaces in the string and putting up an error message? That takes more work than doing the right thing. People are actively wasting their time by doing development work that is utterly unnecessary because they forgot who's at the top of the stack. You are. I am. We are human. This is how I write numbers. If your software can't handle how I write numbers, that's not my problem. Don't give me a red message. People forgot that there's a human being. It's a very easy thing to do. Now, of course, some domains are subtle. There are other examples. So last October, I took the train from London to Brussels. My app tells me that my 2-hour trip will take 3 hours. Oh, there's a time zone change. Apparently, whoever wrote the software to deal with timetables was unaware of the existence of time zones. Time zones have existed since the middle of the 19th century. The train that goes from England to France has existed for about 35 years. The web did not exist. So this software is a lot younger than time zones, trains, and the tunnel. This is a known thing. I also made this observation, gentlemen, if you're holding dates and times without either converting to UTC or also holding time zone data, you're doing it wrong. I mean, I admit, time handling, as I've observed in 97 things every Java programmer should know, the most obvious lesson is that date time handling is harder than people expect, even when they're expecting it. A very simple way of looking at it, if you think you understand how to do date and time handling properly, you are probably wrong. If you think you don't understand everything involved, you are probably right. There's lots of subtleties, but they're all known. They are knowable. This is an S-type system. We should be able to do these. But what about P-types? Acceptability of a solution is determined by the environment in which it is embedded. In other words, in advance, we don't necessarily know what the right answer is. And we therefore don't know how to accept it, and we definitely don't always know how to generate it. Now, this was written in 1980, and the examples he chose were not particularly compelling. But these days, it's a lot easier to find P-code, or rather, P-type programs. Machine learning. This is your machine learning system. Yep, you pour the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Yeah, well, you just stir the pile until they start to look right. I'm sorry if you work in machine learning, and I've just given away your big secret. This is the truth. In other words, what we're doing is we're both creating our requirements and creating our acceptance criteria, and we're creating the mechanisms that do it. But we don't understand the mechanisms. But we're creating them nonetheless. And this is an interesting thing, because it does depart. If you saw Michael Feathers' keynote this morning, there is an idea here that it departs from our normal model of reasoning. I actually did a talk for Code Camp during the pandemic, an online one called Unreasonable Architecture, where I talked about the fact that the difficulties that we have is that we are unable to reason properly about such systems, because they are not built with intention, and they are not built with knowable structure. But this is an interesting thing, because it also takes us back to the word algorithm. A lot of people have started using the word algorithm to describe machine learning systems. Let's be absolutely clear. That's nothing to do with algorithms. That's to do with data. The algorithms are actually quite easy. It's a bunch of linear algebra. It's a load of matrix multiplication. That's it. It's the data that is the hard bit, and understanding the structure that we generate from that data. So let's talk a little bit about algorithms. I want to talk about a really interesting algorithm called permutation sort. If those of you who did computer science degrees will have undoubtedly been taught a number of different algorithms, quick sort, merge sort. You were probably never taught permutation sort because it has terrible, terrible performance. It's what we call an esoteric algorithm. It's fun, but it's not practical. It's not safe for work. It takes factorial time. If I have a list of 10 items, then I'm kind of looking at about 3 million possibilities. Because literally what you're doing is you're going through every single possible arrangement until you hit the one that is sorted. This is a terrible algorithm, but it's great fun. Now, this is great fun to play around with in different languages. I have it as part of a number of other talks and blog articles. And I've implemented it in a number of languages. I've implemented it in Python, I've implemented it in C++, I've implemented it in Groovy. But a couple of weeks ago, I was asked to give a keynote in Amsterdam at Kotlin Conf. Now, I'm not a Kotlin programmer. I actually told them this. I said, I don't write Kotlin. I'm not even properly a Kotlin tourist. And they said, that's fine. We want a kind of big picture talk. That's fine. But I had in this talk an implementation of permutation sort. And I thought, OK, well, let's rewrite permutation sort, because I understand the algorithm. Let's rewrite it in Kotlin. And I thought, you know what I need? I don't really know the library. And I Googled for the things that I needed. Because in Groovy, in Python, in C++, these all have in their standard library a way of generating permutations. And I Googled for this in Kotlin, and I couldn't find it. And I thought, oh, maybe I'm missing something. So I took to the internet. I went to Twitter, and I asked people questions. And people said, oh, well, yeah, here's how to do it, Kevlin. And none of them were the standard library. But then somebody gave me a suggestion. ChatGPT. Hey, ChatGPT, does the Kotlin standard library have a way to generate permutations of a list? Hell yeah. Kotlin standard library provides a way to generate permutations of a list using the permutations function. Awesome. I've got an example of usage. And this will output, apparently, C#. That did not inspire me with a great deal of confidence. And then it gave me other details. Note that the permutations function returns a sequence of lists. Oh, OK. Where list represents a unique permutation. This means the permutations are generated lazily. The use of sequence in Kotlin allows lazy evaluation. It means we don't have to generate millions of permutations in advance. We can generate them on demand until we find the right one. Hey, this sounds pretty good. This is exactly what I want. I want to be able to do that. So that's going to give me an algorithm that looks something like this. For my permutation in this permutations sequence, what's the condition? I need it to be sorted. Okay, we'll look at that one next. Return the permutation, otherwise return this. In other words, there was nothing there. I probably got an empty list, yeah? That's the only circumstance we need to care about. Okay, so what about is sorted? Does the Kotlin standard library have a way to check if a list is sorted? Yeah. You can use the isSorted extension function available on the list interface in the standard library, and here's the usage. This all looks good. So in other words, that's my algorithm. For each permutation, in all the possible permutations, if it's sorted, return that permutation, otherwise return this. In other words, it was empty. Great, this is fantastic. I can tidy it up and make it a little bit more Kotlin style. That's great. Our work here is done, except for one small problem. This is a complete hallucination. This is ChatGPT is totally tripping. Permutations does not exist as an extension method at all. Neither does isSorted. It totally made it up. If we were to talk about ChatGPT as a person, we would say that it's a bullshitter. It's a sociopathic, very well-informed bullshitter, but you can't tell when it's telling the truth. I mean, everything it said is actually idiomatically Kotlin, except for the fact that it's not Kotlin. So anyway, I took its suggestion, and I said I will implement isSorted as an extension method. And I borrowed one of the implementations that I used in Groovy or Python, and I used that as the basis. I then also asked it, hey, could you generate me the permutations function you promised me? And it did, and it didn't work. It didn't do anything right. So we had a little conversation, me and ChatGPT, and I took its code, and then I adapted it, and then it didn't do the sequence thing, so I eventually ended up with a version of this. Oh, I was very pleased with this version. So at that point, I was using ChatGPT as almost a pairing partner, but it was not a very good pairing partner. It would say, here's a piece of code. How do you feel about it? I feel great about it. You do know that it doesn't work. Oh, I'm sorry about that. Now, I'm not going to pretend that I can tell the future. In fact, I often make forecasts that turn out to be wrong. But one thing I can claim is that in 2016, I did a talk in Poland at MobiConf, and I was asked in the Q&A, what is the future of machine learning and developers? And I got it right. Here it is. So we fixed that. If we combine deep learning into that, the whole approach of thinking about development, that's the context I'm talking in, the idea of actually having something that is intelligent assist us, that's going to be really cool. I think that's one of the directions we're going to head in. Yes, we have. There's a lot of other stuff that can be generated, and then this is the important bit. Then we evaluate it. We, the humans, are the reviewers. I made a point about the fact that we need to get better at testing. If you are not very good at testing, then you're going to have a bit of a problem with machine learning. Because that's the thing you need to do. It's like, I see what you've generated for me, now I'm going to test it. The human element will remain. The balance will shift. Your work, the balance, what will future of development involve? It will involve being able to specify something precisely and verify whether or not it was correct. In other words, software development is not going to change. Because we should have always been doing that. But the balance of how we do that will change, just as it always does. So what are we talking about here when we hit the next level? Because when a lot of systems, social media systems and AI systems, are what we would call E-systems or E-programs. Programs that mechanize a human or societal activity, the program has become a part of the world that it models. It's now a feedback loop. You take from the system, you change your behavior, that becomes input into the system. Many social media systems look like this, but we also see it in terms of markets. We see it in terms of learning systems. These are much more complex. They don't submit to being simple algorithms. Now, there's an interesting one here. When we think about this, how does this relate to things like low-level programming? Because I've just gone off the top of the stack into the world. But what about the lower level stuff? So when JavaScript programmers tell me, oh, we don't need to know systems programming, I want you to remind you of Meltdown and Spectre, which hit a lot of Java systems a few years ago, a lot of web-based stuff. These are classes of error that come about from the hardware. And if you don't understand what's going on in the hardware, you'll be more surprised by this than not. There is this idea that low-level programming is good for the soul. So, yeah, let's talk about C. Because that's what the universe is made of. The universe is written in C. It's zero-based. This is the lowest level. I'm sure it's lower than quantum mechanics. C is fundamental. Everything is built out of it, ultimately. But this also gives us some surprising classes of error. This is the POSIX standard. There is a time function that is fundamental to many systems. And even if you're experiencing this in JavaScript, somewhere down here, if you're looking at today's date and time, somewhere down here, there's a little call to time. Returns the value of time in seconds since the beginning of time, 1st of January 1970. Okay? I kind of like the fact that I was born before the beginning of time, and presuming that I survive until the year 2038, that's when 32-bit signed time runs out. Let us assume that there is not an apocalypse. If you want to set your clocks, I think it's January the 17th. It'll be in the middle of the night. If I survive past that, then I will have been truly immortal, because I will have existed before time and after the end of time. Which is a nice thought. But let's look at this from a different point of view. When is the epoch? 1st of January 1970, how do we know this? Because we see it in lots of places. Yeah? Sometimes it's a failure mode. In this particular case, I've been told that drivers, Intel drivers, actually, in a lot of systems, there's a default driver that is basically put in at the 1st of January 1970 so that you will always have a driver. It makes sure that in terms of dates, everything is correctly ordered, but this is the last one that could possibly be chosen, which is quite a cute trick, but it is a little misleading. Intel did not really exist in 1970. Not in the way that we know now. I've just been talking about social media systems, and this is an interesting one. Facebook apparently responded to my error when I submitted, hey, you got a bug. They responded to it back in 1969, which is kind of cool. 31st of December, 1969. How did we get back to that point? Well, there's a really interesting thing here. Let's look at the C standard. The value -1 is returned if the calendar time is not available. This is the most likely explanation for why it is that we ended up in 1969. That what actually happened was the time was not available. Now, I want you to think about that for a moment, because normally you never worry about, when you create a date object or you query a date time for the time now, you never think that that could possibly fail, because in your head, time is always available. But that's not how it works. Time is an operating system feature. It can fail. And in this case, it did. And it returned -1, which was incorrectly. There was no error checking. We called a function, we didn't check the error. I'm sure you don't do that. And -1 second is in 1969. The philosophy that we need to adopt here, we can actually take from the Amelia Brand character in Interstellar. She observes that we need to think of time as a resource. That's how you need to think about it. That's why you don't use global time in your code. You don't sit there in a line of code and say, I'm going to pluck time from the universe. You pass time in like you pass other resources. Here is the resource. It is fallible. It can fail. It's not very likely, but it can. So what happens in these failure modes? Well, certainly we don't want to be reporting things in terms of -1, but we see these kind of failures everywhere. Thank you, Lufthansa, for telling me that nan is not a number. This is the other way people find they express things. Floating point numbers. Hey, there's no number that represents this. Now, this one was irritating and annoying because I was trying to book a flight. This one is potentially more critical. This is an E-type system. It's a control system because it can affect people in the real world. Driverless car, race car, drives straight into a wall. This was in the first year of the pandemic, 2020. During the initialization lap, something happened which apparently caused the steering control signal to go to NaN, and subsequently the steering locked to the maximum value to the right. When I retweeted this, somebody said, "Are you telling me they are writing software for cars in JavaScript, which is enough to make you walk?" And I said, no, actually it's written in MATLAB. But the point is that NaN is not an artifact of JavaScript. NaN has been around since the 1980s. It's built into the floating point standards that we all use. But the point there is there was a failure. It was not accounted for. We are not very good at accounting for the states that our code can be in. Have you ever had that? You open something up, and it tells you, you have no stuff. This is very frightening. Sometimes you go in and you go, oh yeah, my library of things is empty. Where did my stuff go? My orders have all disappeared. And then a moment later, it updates and your heart returns to normal. Why does it do this? Because we don't have a good grasp of state. There's been a fundamental misunderstanding. Because it's not that you had 0 orders, it's that we don't know how many orders you had. Because we haven't looked, because we're waiting for the database. But people have made they have confused themselves. As John Carmack notes, a large fraction of the flaws in software development are due to programmers not fully understanding all the possible states their program may execute in. This is how effectively the model. So this is knowable. This is interesting. This is actually knowable, and yet we've turned it into an error mode or a bad user experience. What they've done is they've said, I've created new information, something that is new, and it is displayable. Currently, all the fields are set to 0. And then the data is loaded, and we update it. This is completely the wrong way to program. There are 2 states here. You create an object. The fact that the order's length is 0 is irrelevant. Why? Because you're not displaying it. Because you don't know the answer to the question. You don't know how many orders there are. The answer is not 0. The answer is, I do not know. And then you get a loaded event, at which point you do know. At that point, you display. What does this look like from a user experience point of view? It looks like this. There you go. That wasn't very hard. Yet almost every website that I go on gets this wrong. They show you they communicate false information to you. Okay, I did this the other day. A bunch of Meetup meetings that I had arranged. I went on to Meetup. I'm not picking on Meetup. If anybody from Meetup is watching this, you're just as bad as everyone else. You're not special. And it told me that I had no meetings, and then I had no meetups, and then it told me I had some. What I'm trying to tell you here is you don't need machine learning to bullshit you. We've created systems that already bullshit to us. We don't need advanced technology to create bullshit. We do it very easily by not understanding the states of our code. So 97 things every programmer should know that I edited a few years ago. Nicholas Nielsen had this lovely piece, Thinking in States. In most real-world situations, people's relaxed attitude to state is not an issue. Unfortunately, however, many programmers are quite vague about state too, and that is a problem. And we see this everywhere, this failure to accommodate state. So one of the things I'm known for is error screens. People tweet error screens at me, and I retweet them, because it's kind of fun, it's interesting. It helps highlight some of the issues that we have in the world, but it also reveals the programming constructs beneath the systems that we use every day. And Martin Fowler messaged me, he atted me on Twitter, you ought to know that United may have discovered a kink in the time-space continuum over the Atlantic. Sadly, they weren't able to take advantage of it and get me home earlier, because you might see that the time to the destination is 0, but the distance to the destination is over 2,500 kilometers. That would be impressive. Because the distance, you see, from Heathrow to Newark is over 5,500 kilometers. Let me put that another way. That's not 19 centimeters. That's 19 light milliseconds. This is the point where when we start thinking about the stack, we also have to respect the fact that in software, we often think of ourselves as working in an abstract space. And we kind of forget the physical world. The problem is that physics cannot be beaten. If you have somebody who says, our servers in London and our servers in New York need to be within 10 milliseconds of each other in terms of data quality, the answer is no. If somebody says, oh, but you're not trying hard enough, you just need to try. It's a matter of attitude. You need to have the right passion. No, my passion will not travel twice the speed of light. You cannot break the laws of physics just to enable your servers to be in sync within 10 milliseconds. Or you could tell your boss, sure, let me just collect my Nobel Prize first, and then I will come back and write the code. This is a point about distributed systems. So a number of years ago, me, Frank Bushman, and Doug Schmidt wrote some books on pattern-oriented software architecture. And this one, in particular, Pattern Language for Distributed Computing. It's where we gave the definition of a distributed system is a computing system in which a number of components cooperate by communicating over a network. It's a very true definition. It's also a very boring definition. We actually opened the chapter where we defined distributed systems with a quote from Leslie Lamport, which is much more exciting. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. There we go. That's a practical, everyday definition of a distributed system. I can't get my work done. Why? Because something somewhere else is not working. And this has some impact. So my other publisher, O'Reilly, they have forest fires in California as an annual, it's an annual event in California. And it turns out that they have issues. It means that somewhere else on the planet, you can't read your book, even though it's supposed to be your book. Actually, it isn't. It's not yours. You're borrowing it. It's a very different relationship. Now, this, importantly, is something that we need to respect when we look at our systems, because there are laws that are governing our systems. Not just the laws of physics. There are laws that define what is knowable. Brewer's theorem, perhaps better known as CAP's theorem, and it is a theorem, it was proven. It's mathematically sound. I think it was proven in 2002, 2003. If you've not come across CAP's theorem, basically it's about your data consistency, availability, and partition tolerance. The last one will need a bit of explanation. But what we're saying is that in a distributed system, there is data. If you request that data, what is the quality of that data? What are you expecting as your response? We see this with social media systems. If I update with a post on social media, and then you go and look at that website, the idea is that you see my latest update. If we're standing next to each other, consistency tells you that what I'm seeing is what you're seeing. Okay? You don't see my old post, you see my new post. This is important for things like bank accounts and stuff like that as well. Availability, oh yes, by the way, consistency, there's another side to it. We either get the same answer, or you're looking at yours going like, I'm not getting a network signal. You get an error. You either get the same result as me, or you get an error. Availability is slightly different. Availability says you will always get an answer. But there's no guarantee it's up to date. But you won't get an error. You could be standing next to me and saying, well, I don't see the latest post, I see your previous post. Partition tolerance, which should have just been called tolerance, is about the idea that it is in a network, a partition is where one part of the network cannot access another part. Yeah, a server goes down, a router goes down. And the idea is you can have any two, but not all three. Consistency and partition tolerance. You're either seeing the same thing as me or you're getting an error. Availability and partition tolerance. We might not be seeing the same thing, but you're always getting a value, even if it's out of date, but you're not getting an error. There's a limiting case, consistency and availability, which is interesting. It means you're always getting the right answer, and there's never an error case, except for the fact that if anything crashes, you get nothing. This is the limiting case of a non-distributed system. Now, what does this mean? It means the fact that you cannot have all three at the same time is a limit on what you can know. I mentioned quantum mechanics earlier. This CAP theorem is kind of Heisenberg's uncertainty principle for the network. Heisenberg's uncertainty principle basically states that you cannot know the momentum or the velocity, as it were, of a subatomic particle with great precision and also know its position. You either know a lot about its position and not a lot about its momentum, or vice versa. There is an uncertainty. You cannot know both to high fidelity. While we're on the subject of quantum mechanics, this is Schrödinger's cat. The cat is either dead or alive. Do we experience this in software? Yes, we do. Have you ever had this? I get this one all the time. I go and look at a site, and it tells me, you have 2 orders. And then you look, there's 3. I've seen that with Gmail. You know, you have 10 emails, and then I look, and it said there's 11. I can see there are 11. You can do it with a lot of sites. They will tell you, you have 2 of these, and there are 3. They're on the screen. There is a list with 3 things in it. Why do we have such errors? Well, perhaps it's micro front ends are to blame, but we've had these problems for a while. The point is that we're getting our data from 2 different paths. They are not consistent. Okay? What's the right answer here? Because sometimes I've had people tell me, oh, but this is to do with eventual consistency. No, it isn't. It's nothing to do with eventual consistency. Because the answer is, if you are showing 3 items, the correct answer is 3. Even if you had a separate query, tell me how many items there are, and then send me a list of the items, that's a pointless, by the way, that's pointless to do. You just need 1 query. Give me all the items you have. What's the length of that? Don't do 2 separate queries that follow 2 different data paths. That's wasteful. But it also means that you also know what the right answer is. If you are displaying 3 things, the answer is 3. It is not 4, it is not 2. The point here, it's a true feature of a distributed system that it may not be in a consistent state. But if you are in the same piece of code, you already know the answer. You are not distributed. I am sitting in the front end. That is not a distributed system. There is only one answer. You choose the one that you're displaying. So what we're hitting here is a limit, fundamental in mathematics. And there are lots of fundamental limits in mathematics, computer science, and physics. Gödel's incompleteness theorems are one of the interesting ones. Many people have come across these. They're also described in that book, Logicomics, that I mentioned. But most people don't think that they're applicable to what they do in code. The idea is that there are statements that are true in a system that cannot be proven to be true. Let's see where that takes us. First of all, there's a bit of history here. As I mentioned, Russell. Bertrand Russell and Alfred North Whitehead tried to unify all of mathematics and show that it was consistent and complete in 1911. 20 years later, Kurt Gödel blew that apart. What is interesting is this idea from a machine learning perspective. As Adrian Collier observed, one premise of many models of fairness in machine learning is you can measure or prove the fairness of a machine learning model from within the system. But what we're saying is you can't do that. You can't use the things in the system to prove a property of the system. You have to step outside that system. Do we see this elsewhere? Well, yes, we do. Let's end on an observation about the real world. It's 2020, There is a pandemic. The streets are empty, except for an artist named Simon Weckert in Berlin, who has 99 Android phones. And he's put them in a cart. And he is now walking around the empty streets of Berlin, causing traffic jams. 99 second-hand smartphones are transported in a handcart to generate virtual traffic jams in Google Maps. Because Google Maps is saying there are 99 smartphones, they are all on the same street, and they are moving slowly. Therefore, traffic jam. This is a reminder. We must be careful not to confuse data with the abstractions we use to analyze them. We confuse ourselves. We bullshit to ourselves. Do people talk about engagement? We have good engagement on our website. Can you measure engagement? I mean, engagement is about a personal state. It's the state of being engaged. It's emotional involvement or commitment. I might even be passionate about it. Engaged is in my head. You don't have access to my head. How do you know that I'm engaged? How do you know that I don't just have the page open and I'm doing something else? You don't. You have no idea what the engagement is. Every time you use the word engagement, or one of your marketing people does, always remind them, we don't actually know the engagement. We just have correlated numbers. What we're actually measuring is clicks and shares. And we're trying to deduce. Now, 99% of the time we might be right, but 99 phones might be wrong. That's the point here. It's just to remind yourself you don't know what the reality is. You have no idea if there's a traffic jam there unless you have a camera. You know there are telephones, you don't know there are people, you don't even know there are cars. Unless you are actually observing that street, you don't know that. Unless you are observing the people using your website, you don't know their state of engagement. This number is very easily gained. Be very careful with this term business value. You can't measure that one either in the same way. Be very, very careful with it. So I will end on this point. When we talk about the full stack, we need to ground it in reality. There is our technical area of focus, our area of expertise. Maybe your full stack is front-end and back-end of a web-based system or a mobile-based system. Maybe you are lower down. Maybe you have a different role in the organization and you embrace perhaps the world of the customer. But the idea is that all of these are interconnected. The full stack is very, very deep because it defines a reality. If you try and ignore it, it will cost you. Thank you very much.